optimal health for high performers. This is the Health Upgrade Podcast with Dr. Nawaz Habib.
Hello, everybody. Welcome back to the Health Upgrade Podcast. This is Dr. Habib here with JP. How are you, JP?
Doing really well. Thank you.
Wonderful. So we are going to dig into metabolic disease. Metabolic disease is an epidemic present on all continents and is worsening in nearly every country on the planet. Technically, it is a spectrum of serious medical conditions, all of which arise in individuals with high body mass indices or BMIs, and more specifically in those with high percentages of body weight attributable to fat. The medical conditions that we are talking about range from type 2 diabetes and hypertension to atherosclerosis, stroke, and a dangerous liver condition that used to be primarily associated with alcoholism called steatohepatitis, which leads to cirrhosis, liver failure, and death. In fact, non-alcoholic fatty liver disease and non-alcoholic steatohepatitis, or NAFLD-NASH, are now larger contributors to cirrhosis of the liver than even alcoholism. In 2018, Mohammed Saklayan published a paper that cites the fact that over 1 billion people in the world are now affected with metabolic syndrome, that obesity also contributed to 120 million disability-adjusted life years, and that finally, between 1990 and 2015, global rate of death related to high BMI increased by 28.3%. Overnutrition, as the experts call it, is one of the costliest in financial terms, as well as human lives, self-inflicted injuries, along with drug abuse in our society today. We have talked about this in several of our prior podcasts, but the importance of the topic made us both want to revisit this in this mini episode. And so we're here to distill a lot of that scientific and clinical information down into something we hope will be a little bit more easily absorbed. And so let's start off with our understanding of what adipose tissue is and how its dysregulation can lead to so many other problems.
Sure. Adipose cells are a great place to start. They're at the heart of the inflammation that dysregulates metabolism in this state of too much fat storage. You see, adipose cells are designed to store energy for later use, and they store energy in the form of liquid fat or a lipid bubble in the middle of the cell. They can release those lipids into the bloodstream during periods of reduced food availability or extended energy expenditure. In a sense, they're like a retirement account that gets bigger and bigger while the person's working or depositing money into the account, but the account might need to be used for periods of unemployment. Unlike a retirement account, however, we do not want to see fat cells continuously growing in size. When the adipose tissue cells grow too large, they can become a serious threat to our health, causing inflammation and disrupting the homeostatic balance.
And how does the immune system relate to these adipose cells?
Well, just like most tissue types, adipose cells have finite lifespans. If they're lean, which means they have relatively small lipid bubbles, when they reach the end of their cellular lives, they die relatively peacefully and are replaced by new cells. This replacement is facilitated by tissue-resident macrophages that are interspersed among the adipose cells. And these are the same innate immune cells that we've talked about so frequently on the podcast. And they're tasked with clearing out the dead cells and promoting the production of new adipose cells from progenitor cells. These progenitor cells react to the macrophage's healthy non-inflammatory signals. This is a similar process to what happens in many other tissue types. For example, red blood cells are a good example, since hundreds of billions of them are cleared out and the hemoglobin and iron is recycled every day in every person on Earth. The difference with adipose cells is that they are atypically large, so that even when they're lean and they have a small fat bubble, they're still on the edge of the size of debris, when they're dead, debris that macrophages can clear away all by themselves and still do it in a non-inflammatory way. That means the size of the fat bubble is everything. Once the adipose cells get too large, their deaths cease being normal debris clearance and as like a housekeeping task, and it becomes more inflammatory. So it can't be done in a non-inflammatory way. It requires shifting into an inflammatory state.
And worse yet, those macrophages that attempt to clear the necrotic adipose cells that were previously filled with lipids end up as lipid-bloated macrophages that are unhealthy as well. We see that excessive lipid levels inside macrophages cause them to get a foamy appearance and ultimately to become dysfunctional and die themselves. This leads to the recruitment of additional macrophages. In the case of adipose tissue, an entire region of necrotic adipose cells and struggling macrophages will form. And these areas are highly inflammatory, and they actually block the production of new adipose cells and create a chronically inflamed state, and circulating lipid levels rise as the storage function starts to fail. And the lipids that end up in circulation can end up being stored in excessive amounts in the liver and other organs. And as we've spoken about on previous podcasts, this inflammatory signal also causes a number of distant changes in organs, including the liver, but also the kidneys and blood vessels, to collect fat and become dysregulated. For example, the liver begins to produce more glucose, leading to chronically high blood sugar levels, which damage circulating proteins, and the excessive fat levels will also cause damage in the liver. So let's look at each of these in turn.
Yeah, as you were saying, it all starts with the inflammatory signaling and high lipid concentrations spreading throughout the body. The inflammatory signals are generally sent in the form of circulating chemicals called cytokines, like TNF-alpha and IL-1, which is an interleukin, and also IL-6. These chemicals trigger some cells, like adipose cells and muscle cells, to respond to that signal by shielding themselves from this inflammatory pressure. And they do that by producing proteins that block cytokine signaling. The thing is that these same proteins also disrupt the cell's ability to take up glucose. And this means that the liver is being told to make more glucose, but the fat and muscle cells are becoming insulin resistant and glucose intolerant. And these are the hallmarks of type 2 diabetes. This stresses the pancreas and forces insulin levels to rise as the body tries to push the high glucose into those cells despite them resisting. At some point, the pancreas will fail, and then you become insulin dependent on medication. Ultimately, the sugar that's floating around in the bloodstream gets caught in the kidneys, and sugar levels in the urine starts to rise.
Hence diabetes mellitus, because we have sugar in the urine, and that sugar that's going through the kidneys causes stress on that organ as well. And that contributes to dysregulation of the renin-angiotensin balance. And what follows? Hypertension.
Exactly. And hypertension, pervasive inflammatory signaling, high lipid concentrations in circulation lead to other problems, such as lipid transport across the arterial wall. You were mentioning foam cells in the context of adipose tissue, but the same thing occurs in the context of lipids being transported through the arterial wall. In circumstances where inflammation is high, there's a heightened reactivity among the vascular and perivascular macrophages. They're in this hypervigilant state that live in the sidewall of the artery in a region called the tunica intima, which is sort of between the innermost endothelial layer and the smooth muscle cells that form the outer tough layer of the artery, and they're present to constrict and open blood vessels as the body needs. When these macrophages become hypervigilant, they begin to engulf the fat being transported across the intima. And over time, they become foamy, dysfunctional, and ultimately they become necrotic themselves. Along the way, they're pro-inflammatory, and they're signaling for circulating monocytes to enter through the sidewall of the artery into the intima and become recruited macrophages. Now, we've encountered recruited macrophages before and have described them as being much more likely to become inflammatory than the resident macrophages that are present all the time. However, in the state of high circulating lipid concentrations, hypertension, and systemic inflammatory signaling, all the pieces are present to make the macrophages, both resident and recruited, inflammatory.
So to review, it begins with excessive fat storage demands being placed on the adipose cells. That leads them to become too large for normal debris clearance mechanisms when natural cellular turnover does occur. Progenitor cells would normally replace those adipose cells that die, but to do that, they require signals from non-inflammatory macrophages. But the macrophages that were tasked with clearing these excessively large fat cells begin to shift into a pro-inflammatory orientation. That leads to a systemic inflammatory signaling that is high, and high lipid levels enter circulation. These cause the liver to produce more glucose than is needed, the pancreas to be under stress to produce more insulin, the cells that would otherwise use up the glucose become intolerant of the glucose and unresponsive to the insulin as part of their own attempt to protect themselves from the consequences of the high inflammation levels. This is called insulin resistance. Next, the organs become overloaded with fat and lipid levels, disrupting their ability to function normally, leading to conditions like fatty liver, hypertension, and kidney disease, and even fatty heart. Atherosclerosis arises as a consequence of macrophages being activated and the excessive lipid transport across the artery wall.
Exactly.
There is another important piece of this metabolic disease condition, and it is the topic that we have spent much of the past season talking about. It is the autonomic nervous system. As our listeners will remember, the autonomic nervous system is a portion of our nervous system that controls and influences things that we don't consciously control, automatic processes. It is everything from our heart rate to our immune system, brain function, gut health, and even metabolic function. And it is the ability of the autonomic nervous system to modulate immune function that matters in this context. Let's start with a quick review of how the autonomic nervous system modulates immune function.
Sure. And since we usually talk about this in the context of the parasympathetic nervous system, and specifically the vagus nerve, which can inhibit inflammation, let's switch things up a little bit and talk first about the sympathetic nervous system, because its activation can actually make inflammation worse.
Yeah, absolutely. The sympathetic nervous system is responsible for the fight and flight and freeze responses of our autonomic nervous system. It triggers the heart to race and pump harder, for breathing to become rapid and shallow. Digestion will slow, and the stomach and intestines will actually constrict. Blood vessels in the muscle will dilate, allowing blood to flow to the muscles so that we can fight or flight, run away from the issue. Sweat glands will increase secretion. We often get sweaty in that scenario when the SNS is activated. And the kidneys will raise blood pressure in arteries and even dilate your pupils so you can see the threats and ways to get away from the threat more readily. And it's pretty easy to see how short bursts of that sympathetic activity provide for better performance, whether in brief athletic events or even life-threatening circumstances. But over longer periods, the symptoms of chronic sympathetic activation, including anxiety, hypertension, depression, autoimmune disorders, cancer, and diabetes can occur. In fact, in a paper that is nearly 2 decades old, it was written that primary aging in adult humans is associated with a progressive tonic activation of the peripheral sympathetic nervous system, or SNS. The purpose of the SNS activation and its physiological impact are, however, unknown. We hypothesize that the chronic stimulation of the SNS with aging is driven in part by a progressive accumulation of body fat. This error is sensed by the central nervous system via increases in adiposity-sensitive humoral signaling, these are both inflammatory and metabolic, that cross the blood-brain barrier, activate subcortical areas involved in the regulation of energy balance, an example would be ventromedial hypothalamus, and stimulate the SNS outflow to peripheral tissues, essentially activating the sympathetic outflow more readily.
Yeah, and higher sympathetic outflow enhances inflammation, as Pancreas and Straub wrote about in their 2014 article called The Sympathetic Nervous Response to Inflammation. They said the activation of the sympathetic nervous system results in the release of sympathetic neurotransmitters, norepinephrine, ATP, neuropeptide Y, and nitric oxide. All neurotransmitters have direct influence on immune cells, although sympathetic influence on immune cells can be direct via adrenergic receptors on immune cells, or indirectly via regulating blood flow or lymph flow, regulating the distribution and production of lymphocytes, or modulating the release of pro-inflammatory peptides. Inflammatory cell recruitment and redistribution is also controlled by the SNS, or the sympathetic nervous system. For example, the role of the SNS-dependent monocyte recruitment from the spleen in experimental peritoneal infection. In addition, the generation of some white blood cells in the bone marrow is influenced by the sympathetic nervous system, resulting in preferential production of pro-inflammatory white blood cell populations.
Exactly. So short-term activation of the sympathetic arm of the autonomic nervous system can be beneficial or even necessary, but chronic activation leads to chronic inflammatory pressure. It is no wonder that the chronic inflammation that's related to adipose tissue dysregulation is associated with high sympathetic activity.
For sure. So it's a bidirectional relationship, with chronic inflammation leading to sympathetic overdrive and chronic sympathetic overdrive leading to heightened inflammatory pressure. But the other arm of the autonomic nervous system is the parasympathetic, or the vagus nerve, and it's associated with the opposite of fight, flight, and freeze, which is rest, digest, relax, and restore modes. One of the most important medical discoveries of the last century has been the recognition that activation or even stimulation of the vagus nerve, which is the parasympathetic arm of the autonomic nervous system, has the opposite effect on the immune system from what the sympathetic arm does. That is, that stimulation of the vagus nerve quiets the innate immune cells, like macrophages, pushing them to return to a homeostatic state in which they remain anti-inflammatory and do their housekeeping tasks more effectively. That involves the release of the parasympathetic neurotransmitter acetylcholine, which binds to a critical receptor we refer to as the A7 receptor, the activation of which triggers a series of pathways that reduce the production of and the effects of pro-inflammatory signaling within the cell. This happens at multiple locations within the cell, including at the nuclear level, where the transcription of inflammatory genes is inhibited, as well as within the mitochondria, where calcium ion levels are prevented from causing the release of cytochrome C, which can trigger programmed cell suicide, and mitochondrial DNA release, which can trigger inflammation through multiple pathways, including STING. In the context of metabolic inflammation, stimulation of the vagus nerve has been shown in multiple studies to reduce the activation of adipose tissue macrophages, reduce the liver's forced production of glucose, and reduce the insulin resistance that comes as a result of cells trying to inhibit themselves from being drafted into the inflammation war. The benefits, therefore, span not just type 2 diabetes, but fatty liver disease, and there are remarkable reports of changes in liver enzyme levels after implantation of vagus nerve stimulators for the treatment of epilepsy among people with suspected non-alcoholic fatty liver disease, or NAFLD. Also in hypertension, and there are published papers suggesting that it helps prevent the development of atherosclerosis. There are even studies being conducted to see if vagus nerve stimulation can prevent or even reverse the cognitive decline or cognitive dysfunctions that have been associated with metabolic disease. However, while there are vagus nerve stimulation devices that have been approved specifically for weight loss and the treatment of obesity, it's my personal opinion that the scientific literature about this supports a slightly different interpretation. Vagus nerve stimulation reduces inflammatory signaling that arises from the dysfunctional adipose tissue macrophage failure to clear out necrotic hypertrophic adipose cells cleanly and efficiently. And that should reduce the insulin resistance and glucose overproduction in the liver. However, with those pressures gone, muscle and fat cells become more efficient users and absorbers of energy that's derived from food. That is, VNS can make weight loss easier through more efficient energy expenditure in the muscles, but it also makes storage of excess calories more efficient as well and stops what doctors refer to as the spilling of sugar or calories in the form of sugar exiting the body in the form of urine through the kidneys.
So for the comic book fans out there, as Uncle Ben said from Spider-Man, with great power comes great responsibility. The power is the vagus nerve stimulation technology that can provide that pathway to efficient and healthy weight loss, or just as easily make weight gain more efficient. So if you choose to find ways to activate the vagus nerve, whether naturally through exercise, stretching, humming, gargling, or a number of other physical means, or you use technology like a vagus nerve stimulator, if your goal is to lose weight, you have to also move, build muscle, and mindfully follow a diet.
Exactly. I think a vagus nerve stimulation is a weight loss assist tool. It isn't a drug or a surgery that's going to alter your body's normal function to block calorie absorption or even impair your ability to eat beyond tiny portions. It will, however, drive your immune system to be as healthy as it can be, enabling you to lose the weight more efficiently because there won't be that inflammatory mountain you have to overcome on the way to being that leaner version of you.
Yeah, I love that. I think being able to put the science together here and understand the mechanism by which these metabolic challenges lead down this path, the beginning with the adipose cells building up and then leading to atherosclerosis, leading to NASH, leading to the sequelae and even the cognitive issues that we talked about. Understanding that pathway is really important, and understanding that there is technology, there are tools out there like vagus nerve stimulation and exercises to keep you in a more parasympathetic state that are helpful, but it needs to be paired with some really important work that you can do to optimize the burning of the stored calories within your body.
Absolutely. Again, it's a tool to help you with weight loss, exercises, and other things that you can do physically, including mentally. Meditation is another one. All of these things are very good tools. There's also technologies that can do it. But in the long run, the goal is to keep you healthier longer, to extend your lifespan. And I think that by maintaining a proper weight and maintaining the health of your immune system, you can do that.
Yeah, no question about it. I think this was a really good episode. Nice, short, brief, but full of information. And please take this information, for anybody who is listening, take this information, share it with anybody who you think could utilize it, whether it's a clinician, a friend, a loved one, somebody that needs to understand how they can take that next step to optimize their health and get their health upgraded. Have yourself a wonderful day, and we'll catch you on the next one.